At first light, the mountain does not look raised. It looks left behind. From a distance, its crown sits flat against the sky like a cut surface exposed by accident, and its walls descend in long vertical textures that resemble grain more than fracture. In old survey photographs, before the asphalt pull-offs and the fences and the language that taught people what to call these things, such formations stand alone above plains, deserts, and broken forests like remnants of objects too large to fit the world around them. The official explanation says uplift, erosion, cooling, intrusion, weathering. And in many places, that explanation is sufficient. But in a small number of cases, the land presents something harder to forget. Not a peak. Not a range. A stump. The accepted geological story is orderly. Mountains rise through tectonic collision, volcanism, crustal deformation, and the slow pressure of deep time. Igneous rock cools and fractures. Sedimentary layers harden and tilt. Softer material is stripped away by rivers, frost, and wind, leaving harder masses exposed. Entire plateaus are reduced to mesas. Volcanoes disappear and leave necks behind. Uplift creates relief. Erosion sharpens it. Science has terms for every stage because those stages are real, observed, and measurable. What remains on the surface is the residue of processes that operated for millions of years. That is the official explanation, and it is not trivial. It accounts for a great deal. But there is a difference between an explanation that works in general and one that fully satisfies the eye when the form itself appears unervingly specific. Because some mountains do not merely look old. They look severed. Some stand isolated with broad, level crowns and fluted sides, rising from the terrain not like the top of a buried range, but like the exposed section of a single vertical body. Some narrow upward in ways that feel structural rather than accidental. Some widen at the base in heavy radial flares, with surrounding debris arranged in long angular fragments like peeled shell or collapsed fiber. Some are ringed by ridges that spread outward from a center with a pattern closer to root stress than drainage logic. And once that resemblance is seen, it begins to recur in places that are not supposed to have anything in common except rock. The official explanation describes their material. It does not always dissolve their shape. So the theory, stated carefully, is not that every mountain is a tree. It is not that geology is false, or that maps are lies, or that the earth has no deep history. The theory is smaller than that, and stranger. It suggests that a limited class of isolated mountains, mesas, buttes, monoliths, and columned formations may be the mineralized remains of an ancient biological landscape so old, so transformed, and so far outside modern ecological assumptions that it was absorbed into geology before anyone seriously tested it as anything else. Not myth. Not metaphor. Not a poetic comparison. A physical possibility. A lost forest on a scale no living forest now permits, cut or destroyed before recorded history, buried, petrified, exhumed, and finally renamed. The stone remembers. What changed was the explanation. Begin with the simplest evidence available to anyone with eyes. Form. There are formations across the world whose geometry is difficult to place within the usual categories of mountain building. They do not read as ridgelines, as remnants of broad uplift, or as collapsed volcanic cones. They read as singular objects. A trunk is a singular object. A stump is a singular object. An isolated monolith with a flat crown and vertically banded sides also behaves visually as a singular object, especially when the terrain around it appears secondary, as if it had developed after the fact. This matters because geology often explains through process, while recognition begins with shape. The human mind can be misled by resemblance. That is true. But the mind can also detect pattern before a discipline has language for it. The first witness is often the eye. Then consider proportion. In several well-known formations, the height-to-diameter relationship feels less like random erosion and more like engineered support. The body rises massively from the ground, then either tightens slightly or maintains a coherent vertical shaft before ending in a plateau-like surface. Around the base, there is sometimes a radial spread that resembles buttressing. In botany, large living structures solve stress through widening at the point of load transfer. In geology, many different processes can also create broad bases. The question is not whether rock can do this. It can. The question is why certain masses display several of these cues at once. Central rise, vertical texture, broad root-like flare, and an abrupt top surface that feels removed rather than weathered. A single trait proves nothing. Convergence is what matters. Maps intensify the problem. Look at enough topographic maps and aerial images, and a strange pattern begins to emerge. Some isolated mountains produce contour forms that are almost concentrically organized around a central mass, with drainage and subsidiary ridges extending outward in ways that resemble stress propagation from a trunk rather than the fragmented inheritance of a larger range. In some places, surrounding terrain appears like broken ground around a missing central organism, with smaller outliers arranged like severed projections or companion growths. Cartography does not interpret. It records. And what it records, again and again, is isolation. Not every isolated formation is suspicious. But the pattern repeats in a way that makes coincidence begin to feel like a category of its own. The record is still there. Old photographs deepen that feeling. 19th-century survey images from the American West, Central Asia, Southern Africa, Australia, and parts of South America often show enormous stone masses rising above landscapes of comparatively immature tree cover. The vegetation looks recent, small, transitional. It does not appear to belong to the same scale as the object dominating the frame. In many of these images, the terrain seems half-finished, as if a former order had been removed and replaced by something biologically diminished. Surveyors documented elevation, orientation, rock type, and access. They named towers, buttes, and knobs. They did not speculate beyond the accepted language of the day. Yet the images preserve something their captions do not resolve. A stone cylinder above sapling forest. A flat crown above a young landscape. The absence of fit. The silence of classification. There is also the question of surface texture. Certain monoliths and cliff walls display long parallel bands that geology attributes to jointing, contraction, weathering, and differential breakage. Those are real processes. Still, in some formations the texture is so regular, so bundled, and so vertically coherent that it evokes grain more than fracture. Not proof. Evocation. That distinction matters. But science has often advanced because someone took a persistent resemblance seriously enough to test it. Fossil bone once looked like ordinary stone until context changed. Petrified wood was once just rock with a pattern. Coral reefs were once categorized incorrectly because the biological readings seemed implausible at the scale involved. The question is not whether resemblance is evidence by itself. It is whether repeated resemblance across material, proportion, and landscape should have triggered a different line of inquiry than it did. Measurements offer another clue. On some isolated formations, the vertical ridges extend with unusual continuity for hundreds of feet. Around them, debris fields contain long angular fragments aligned in ways that feel less like random collapse and more like longitudinal splitting. On some flat-topped masses, the upper surface sits with a suddenness that resembles truncation. Below that, the sidewalls descend in orderly planes. In engineering, when a column fails or is cut, certain stress patterns emerge at the point of separation and at the base. No one is claiming direct equivalence. But the vocabulary of structural support, load-bearing flare, and longitudinal fiber has an unsettling tendency to become relevant in precisely the places where ordinary geological storytelling becomes visually least satisfying. What remains is not certainty. What remains is pressure on the official account. To be fair, mainstream geology is not ignoring shape. Geologists are well aware that humans are vulnerable to analogy. We see design in randomness, faces in clouds, and intention in natural pattern. Columnar jointing is a documented phenomenon. Volcanic necks do survive after surrounding cones erode away. Resistant caprock can preserve mesas. Differential erosion can create strikingly abrupt profiles. These are not evasions. They are genuine explanations grounded in fieldwork, petrography, dating, and comparative study. And any serious alternative theory has to survive that. If it cannot, it collapses into fantasy. But there is still a legitimate criticism to make. The prevailing framework tends to decide the category before exploring the full implication of the form. Once a structure is labeled volcanic, erosional, or sedimentary, its morphology is interpreted inside that box. The possibility that the box itself may be incomplete rarely receives serious funding, serious sampling, or serious institutional attention. That is not fraud. It is habit. And habit can hide a great deal. Scale is the immediate objection. Trees do not become mountains. Biology has limits. Water transport, gravity, atmospheric chemistry, nutrient flow, and structural loading all impose boundaries on how large a living vertical organism can become. That is true under current conditions and among known lineages. But the fossil record already preserves worlds that violate modern intuition. There were forests dominated by giant lycopsids unlike anything alive now. There were insects with wingspans now impossible under current atmospheric conditions. There were swamp ecologies that modern textbooks would reject if the evidence had not survived. Deep time is not obligated to resemble the present. Once that is admitted, the argument from impossibility becomes weaker than it first appears. It does not disappear. It becomes conditional. The real question is whether some mineralized forms on Earth were excluded from biological consideration not because they were tested and disproved, but because their size made the category itself feel unacceptable. What if the Earth once supported macrobiological forms whose remains would now be mistaken for terrain? That sounds extreme only because current ecosystems have trained the imagination downward. We think in forests of tens of meters, not thousands. We think in trunks, not mesas. But scale changes classification. A hand specimen of petrified wood is recognized instantly. A hill-sized specimen would not be. It would be geologized on site. The pattern does not disappear. Only our willingness to call it by the same name does. The ground around these formations deserves closer attention than it usually receives. In many locations, the central mass is surrounded not just by general talus, but by broken stone arranged in plates, wedges, strips, and radial fields. Some slopes look peeled. Some debris resembles sheared longitudinal fragments. In satellite imagery, some isolated mountains appear to sit within disturbed zones whose geometry seems organized around the mass, as though the surrounding landscape responded to something once rooted there rather than simply eroding around a resistant core. Again, geology has terms for these arrangements. Scree, exfoliation, joint blocks, collapse fans. The issue is not that these terms are wrong. The issue is that the terms may describe the final condition while leaving the original condition untested. Naming a pattern is not the same as solving it. Then widen the frame. This is where the theory becomes either stronger or weaker, depending on one's tolerance for repetition. If the resemblance occurred in one place only, it would be easy to dismiss. But there are flat-crowned table mountains on multiple continents. There are isolated vertical towers with fluted sides in widely separated geologic settings. There are stump-like buttes in deserts, mesas with radial buttressing, monoliths standing alone above plains, and giant stone masses whose proportions evoke truncation rather than emergence. They are catalogued under different geological histories because their mineral composition and regional context differ. Fair enough. But if a biological world of sufficient antiquity were destroyed, buried, and mineralized under varying conditions, one would not expect uniform preservation. One would expect diversity. Wood does not fossilize one way. Tissue does not mineralize one way. Pressure, chemistry, temperature, groundwater, sediment load, and time would all alter the final form. A lost forest, if it ever existed, would survive as fragments. The pattern repeats, even when the labels do not. There are also peculiar absences. In some alleged volcanic remnants, the surrounding evidence for the former system feels inferential rather than obvious. The cone is gone. The lava fields are gone or distant. The feeder context is reconstructed. That can happen. Erosion removes more than intuition likes to admit. But when the surviving remnant begins to resemble a cut column more strongly than it resembles the afterlife of a volcano, the burden of explanation rises. An object may be explainable and still not be explained enough. This is a subtle point, but an important one. Science is strongest when it distinguishes between sufficiency and closure. Some formations may have received closure too early. Historical timing also matters. Many of these landforms were classified during the consolidation of modern geology, when the discipline was imposing order on a previously chaotic body of observations. That standardization was a major achievement. It gave the earth sciences coherence, predictive power, and practical authority. But every mature discipline stabilizes itself by reducing anomalies, not multiplying them. Ambiguous cases are absorbed into the nearest durable category. Once a mountain is described in a survey as volcanic, erosional, or intrusive, later observers inherit that frame. Guidebooks repeat it. Museums teach it. Tourism markets it. The object itself remains in the landscape, unchanged. Only the permitted questions narrow over time. What changed was the explanation. And this is where the theory stops sounding like simple conspiracy and starts sounding like institutional inertia. Truth is not always hidden by deception. Sometimes it is hidden by filing systems, budget lines, disciplinary boundaries, and the economics of attention. Geologists study rock composition and tectonic context. Paleobotanists study identifiable fossil remains. Cartographers record landform shape but do not adjudicate origin. Museums inherit categories from prior literature. Universities fund research that extends accepted frameworks more easily than research that threatens to scramble them. No one has to falsify anything. No secret meeting is required. A possibility can vanish simply because it belongs to no department. Classification can bury a thing more effectively than secrecy. Bureaucracy leaves fewer fingerprints than conspiracy. Language may preserve older intuitions. Across many cultures, unusual stone formations are associated with petrified giants, sacred poles, world trees, severed columns, transformed beings, or places where the land was cut. Myth is not data in the strict sense, but it is a record of perception before technical language rearranged the world into disciplinary categories. People often responded to these formations as singular bodies rather than ordinary mountains. That alone proves nothing. Yet it means the oddness is not modern. The feeling precedes the theory. Long before geology named these masses, human beings were already treating them as remnants of something that had changed category. The first witness was the eye. The second was story. Only later came the report. There is another reason this theory persists. Certain places simply feel mislabeled. A person can stand beneath one of these monoliths, place a hand against the vertical bands, look up toward the broad flat crown, walk the broken ring of debris around the base, and sense that the official explanation is complete in one register and incomplete in another. Composition may be known. Age may be estimated. Regional process may be described. Yet origin still feels thin. A fossil is stone. That does not make it any less biological. A stump, mineralized long enough, would also be rock. Categories overlap more than institutions prefer. If the theory is wrong, it should be wrong under directed examination, not under ridicule. That is what matters most. The question is testability. Could certain isolated formations be re-examined using methods designed not just to confirm mineral class, but to search for large-scale patterned organization consistent with mineralized biological structure? Could comparative morphology be applied globally to a curated set of flat-crowned monoliths and stump-like mesas? Could base geometry, debris arrangement, radial ridge systems, and surface texture be studied across continents without assuming the answer in advance? Could some of the most visually troubling examples be selected precisely because they fit the geological story least comfortably? Even a negative result would be valuable. It would tell us that the resemblance ends at resemblance. But that work has not been seriously normalized. What is missing is not rock. What is missing is permission. And so the argument compresses into something more unsettling than the theory itself. Perhaps the hidden pattern is not that mountains are trees. Perhaps it is that a small category of anomalous landforms may preserve the remains of a lost biological order, and that modern civilization, for reasons of training rather than malice, has learned to look straight at them without asking the forbidden question. A severed tower becomes a tourist landmark. A flat crown becomes a summit. A radial base becomes erosion. The words are not necessarily wrong. They may simply be downstream from an older reality we no longer know how to name. If that has happened even once, the implications are enormous. It would mean the Earth retains readable remnants of a prehistorical world not merely in fossils and strata, but in the largest objects on the horizon. It would mean some landscapes are not just shaped by life, but are the remains of life. It would mean that what we call geology may, in rare cases, contain biology on a scale that broke recognition itself. The stone remembers. The pattern does not disappear. Then look again at the isolated mountains, the tablelands, the columned towers, the flat-crowned giants standing alone in deserts and plains. Look at the old photographs. Look at the maps. Look at the radial ridges, the buttressed bases, the peeled slopes, the strangely cut horizons. Ask why the resemblance persists across continents and across categories. Ask why some formations feel less like peaks than like sections. Ask why so many of them stand alone, as though whatever surrounded them is gone. Because once the mind admits the possibility, the landscape changes. Not completely. Not everywhere. Most mountains remain mountains. Most geology remains geology. But a handful of forms begin to separate themselves from the rest. They stop looking raised. They start looking exposed. And after that, ordinary explanation has to work much harder to recover its hold. The real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.